por dejarme venir y hablar con ustedes un poco de validación, que es un tema un poquito, le demora a uno un poquito para entenderlo bien, por lo menos a mí, me demoró así, pero es algo muy importante para la citometría de flujo. Okay, why validation? Cell-based fluorescent assays require a passing through a regulatory strategy for review. Okay? The FDA tells us what to do. At the end of the day, the FDA rules. The lab-developed tests arena is something that the FDA has a vested interest in making sure that everybody does it right, because lab-developed tests are the movement of what was previously a manufacturer's responsibility over to passing that responsibility on to you, the lab professionals. Most assays that we use now use lab-developed tests. Let me get a hands up for anybody doing flow cytometry today. Higher, higher. Okay, so not too many, but I'm sure you're doing leukemias, lymphomas, and other flow cytometry assays. There was an absence of well-defined guidelines for this type of validation, especially when using fluorescence detection to quantitate molecules. So, since we use general laboratory practices for all areas of the laboratory, adoption of standardized methods and QC procedure will result in accurate and precise results, which is what we're looking for. So, a little bit of background. In 2011, work began to organize a set of guidelines to basically take the bull by the horns, as it were, and put some definition around this. In September, so 2 years later, September 2013, these guidelines for doing validation were published in Cytometry B. These documents represent a consensus, not just for the US or for Europe, but internationally. And they actually were an improvement over a previous CLSI guideline. As I said, this took 2 years to publish, and it was a result of 40 individuals coming together internationally to create the backbone for cell-based assay development. The trick here was that validation is something that's easy to do on soluble molecules. But when you get to cell-based assays, it becomes a little trickier, and everything doesn't exactly translate one for one. So here I've referenced, so I guess I'm not telling you. Here we go. Here I've referenced the volume of cytometry. I strongly urge you to either get a copy or go onto the ICCS website, or I'll give you some further, as I go through the presentation, other references. You can get this information free. There's a lot of information on the web. This is phenomenal because it's basically your roadmap for how to set up validation in your laboratory. The individuals that were involved in putting this together is quite a distinguished group. Some of these, if you've gone to some of the international meetings or the International Clinical Cytometry meeting or Cytometry meeting, some of these names will be familiar to you. If the names aren't familiar to you, certainly the institutions they come from should be. So, what is in these documents? There's a lot in these documents. It's put together very nicely. It's put together in such a way that it basically grabs you by the hand and walks you through the validation process and helps you establish and build on what you've already done. It covers a wide area of issues, from pre-analytical, so basically soup to nuts, right? It helps you get the thought process started if you've not already done so, on what you've got the request and you've got the result, but how do you set up everything in between to be good manufacturing practices and to be accurate, precise, etc. So let's take a look at pre-analytical issues. And just to be clear, I'm not going to cover everything because it's a lot of information and I've only got 15 minutes. So as we go through this, you're going to have questions. That's great. I will give you this presentation. It'll have the references to the documents. I strongly encourage you to get them. They don't take that long to read. They're heavy documents, but they don't take that long to read, and believe me, you will be very happy that you did so. So, pre-analytical. What's pre-analytical? The sample, what anticoagulant do you use? What kind of specimen do you use? How old is the specimen, etc. Things that you are very well aware of and I'm sure you've thought of in your assays. The sample, there's certain things though that I want to highlight because they're called out specifically in the guidelines. The sample should be appropriate and should have a medical indication for testing. You shouldn't just test to test. There should be a medical indication. The sample type and the collection method should be appropriate, right? If you think there's an involvement of the bone marrow, you should be looking at the bone marrow. The sample should be labeled with at least 2 unique identifiers and must have the date and time of collection. And the test requisition must accompany the sample. Now all of this, these are the guidelines, but you should always check for local regulations as well as your own institutional regulations. Anticoagulants and specimen age. Both are dependent on transportation and storage. So, peripheral blood, you can use a variety of anticoagulants. EDTA is preferred in this instance, especially if you're going to do hematology. So it makes it a good transition to go from your hematology analyzer to your flow cytometer. And if you stop to think about it, it's almost one and the same, right? So Sysmex analyzers, hematology analyzers, are flow cytometers. So you're already doing flow cytometry in your labs, whether you think you are or not. So flow cytometry becomes a follow-on method for taking the diagnosis or the flag that you get with hematology to the next level and profundizando el análisis de la muestra. If you need to use your sample a bit later, let's say you get it at Friday at 5 o'clock, you should always make an effort to run your samples as soon as you possibly can. But sometimes you have bionuclear events and that's important. So you have to be here, right? So maybe that sample, patients come in before you know it's going to be okay to leave it for Monday. In that case, you might use 2 tubes. An EDTA tube for your hematology analysis and an ACD tube for your leukemia analysis, which is good for 72 hours. If you're looking at bone marrow, the preferred anticoagulant there is sodium heparin. If there, unlike peripheral blood, if you use ACD and you don't quite get the ratio of bone marrow to anticoagulant right, because ACD has a lot more liquid in it, you could change the pH of the sample and that might affect your viability of the cells. I see a lot of nodding, I must be saying it right. And if you can't process immediately, check. Some of these samples are precious samples. We don't have the luxury of saying, well, yeah, it was no good, just collect another one. If it's bone marrow, if it's a pediatric sample, you have to respect the patient, right? The patient always comes first. So in the case where you can't abide rigidly to any of these guidelines, do a viability and make your decision based or make your report based on what your viability tells you. Some more pre-analytical issues. Storage, stability, and transportation. For the most part, store at room temperature. Refrigeration or changes to temperature can affect the expression of cell surface antigens. And we don't want to do that. We want to process as native a sample as we can. Viability. Always record your viability either before or during the assay as part of your run. If you've got a fabulous specimen, you can do this. If you know it's absolutely perfect, you can do this with forward and side scatter. That usually gives you a pretty good idea of what's live and what's dead. You don't have any trash down here, everything's good. If you don't, use a viability dye like propydium iodide, 7-AD, DAPI. Use something that's makes sense in your setting. There's no one size fits all. So if it makes sense in your lab, do it in your lab. DAPI is great. PI has its issues. It's a carcinogen, it may be more expensive to get into your lab. So think about all of those things. Get a cell count. You need a cell count to know how much antibody to use, and vice versa. You need to know how many cells you have because you know how much antibody you're using. So there's a proportion of antigen that's required or that's optimal for the performance of the antibody. And usually your manufacturer package inserts will give you an idea of what that is. Adjust it. If it's not right, adjust it. If your sample has few cells, adjust the amount of antibody you use. If your sample has a lot of cells, dilute it with PSA or saline with BSA. And take a look at the morphology, because the morphology tells you a lot. We have instruments now that can automate that for you, which it really helps to have a correlation between what the machine is telling you it's seeing and what you're actually seeing on the slide. Obviously, if you're using body fluids, you're going to use something like a cytospoon. So now let's take a look at some analytical issues. You'll see here, I maybe don't see it very well. I'm not going to touch on everything. I'm going to touch on the things that, in my experience, thinking back to working in the lab, were important to me. Okay? Analytical issues, we need to be clear to monitor for consistency of critical performance. And the factors that do that they're pretty obvious. You know this. I'm not going to tell you anything here you don't already know. Your instrument. Your instrument's not performing, you're not going to get a good sample. You're not going to get a good result. Light scatter and resolution. This is all affected by alignment. It's affected by the purity of the fluids. Howard Shapiro said in his book, garbage in, garbage out. Very true. Basic, but very true. The stability of the instrument is critical as well. If it's fluctuating in performance, it's going to fluctuate in the quality of result that it gives you. Fluorescence is important. Detection of fluorescence. You can use beads or cells to make sure that your fluorescence is performing well. If you're doing any kind of quantitative tests, you need to make sure that your linearity is good. And you need to have a way to check for sensitivity of dimly fluorescent particles, because that's going to be key in some, especially minimum residual disease. Those are expected by electronic noise. So a lot of this is going to be impacted by the care and feeding, if you will, of your instrument. Cell concentration is checked with either, cell concentration is determined with either a volumetric method or a beam, depending on your manufacturer usually. So optimization, and here I think this is where everybody gets excited for reagents, right? Because everybody wants to make sure that the reagents are put together well, panel makes sense, etc. Optimization is nothing else than having proper definition, having thought it out clearly, thought it out well. So it's like when you paint your house, right? You spend a lot of time picking the color. You spend a lot of time covering up all the furniture. You spend a lot of time making sure everything is away from the walls. And then it takes you a few minutes to paint. It's the same thing here. There's a lot of time and effort spent at the front end to make sure that you've got the right antibodies, to make sure that they're in the right fluorochrome combinations, to make sure that they're relevant to the cells and the populations that you're looking for. So that's all very important. It's just preparation. Define your antibody combination, as I said, based on what you're looking for. Do research. Go online. See what other people have done. Research the products. Read the package inserts. There's a lot of information on package inserts. Select a fluorochrome that makes sense. If you've got if you're looking for an antigen that's dimly expressed or that has few molecules on the surface, use a really bright fluorochrome so that you can see it a mile away. If it's the opposite, it has a lot of antigens on the surface, use a fluorochrome that's a little dimmer so that you don't blast everything else into oblivion. Is this making sense? Okay. When you choose your fluorochromes, also keep in mind that some fluorochromes, we're doing multicolor flow cytometry now. The days of two-color flow cytometry are long gone. So now we're doing multicolor flow cytometry with a lot in that tube, a lot of colors in that tube. Choose your fluorochromes and your fluorochrome and antibody combinations such that you manage spectral overlap. You don't want to use two markers that are right next to each other in fluorescence because you may not be able to differentiate those. And be aware of constraints. Okay, I like to say not all antibodies are created equal. Okay, so some antibodies are fussy. Some antibodies change if they're fixed. Some antibodies go away. We mentioned earlier, temperature plays a big role in the performance of your antigens. We're looking at living things, so we have to treat them that way. And that's the fundamental reason why you can't treat a cell-based assay for validation the same way you treat a sodium. It's very different. Fluorochromes as well. So antibodies aren't the only temperamental ones. Fluorochromes as well. Some fluorochromes are dependent or can be altered with environmental conditions like pH. So we have to watch for things like that. Antibody combinations. When you create your panels, make sure that you've got anchor or gating antibodies. That gives you consistency throughout your assay, right? Because what we're shooting for here is good manufacturing practices, good laboratory practices. Because remember, now, you're doing the same things that manufacturers are doing when they provide you, here's an IVD product, this is how you use it. Except you have the flexibility with lab-developed tests to say, okay, here's my assay, I've developed it, I've done all this work, but hey, here's a new novel marker that is better science in my lab. So I'm going to take my lab-developed test, I'm going to pull out this marker, I'm going to put in this marker, and I'm going to do better science. I'm going to give my patients better care. You have the flexibility of doing that. Whereas a manufacturer gets years and a lot more money. Okay? More constraints, or antibody fluorochrome conjugate organization, optimization. You know in your laboratory how your antibodies work. You define acceptance criteria. The manufacturer will tell you this bottle contains this antibody in this concentration, but you define what you consider acceptable performance or not. So you have to set acceptance criteria in your laboratory. Like I said, compare what you're seeing to the literature. Okay? There's scientific discoveries every day, but they're not common. So if you're seeing something different to everybody else, probability dictates that you have to go back and assess what it is that you're doing. So if you're different, see why you're different, and either fix the problem or publish your new discovery. Controls. Controls distinguish between antigen negative and antigen positive populations. Simple, basic understanding, right? They also determine background noise, autofluorescence, spectral overlap, and non-specific binding. They can help with all of that. An internal negative control in leukemias, there are internal negative controls and internal positive controls. And these are cells, populations within the sample that are just naturally positive for whatever you're looking for, or naturally negative for whatever you're looking for. Those are important to take a look at to make sure that your assay and your process are functioning well. Lysis methods. There's usually 4 lysis methods. Here, the middle 2 are, I think, the most common. Stain, lyse, and no wash. That's usually something that the manufacturers provide for you or sell you. Be clear about things. This is good if you want to make sure that your cells, the number of your cells has not changed. Anytime you wash, you have cell loss. Basic science. The amount of cell loss is directly correlated to the amount of times you wash. You wash more, you lose more cells. So if you're interested in a quantitative assay, you want to minimize the amount of times that you wash. If you're interested in a qualitative assay, like leukemia, for example, the leukemia assessment or evaluation, all you're looking for is positive or negative. Positive or negative, bright, dim. So, if you've got one cell more or less, maybe it's not so important. If you're doing MRD, you might reconsider that. Some people also do something called a bulk lyse, where, it's easier. If you're going to do a lot of cells, if you're going to do a lot of tubes, you do one lyse, you have your cells ready to go, and then you just use those, and it's a much faster route. It all depends on what fits in your environment. There is no right way, there is no wrong way. There is what fits in your environment. Remember, these are guidelines. Intracellular staining. If you're doing leukemias, you're doing this. There are varieties of ways to do this. Most of the time, you should be fixing your sample with either a cross-linking fixative like formaldehyde, or a low molecular weight fixative like ethanol, like some sort of alcohol. Permeabilization is usually done with some sort of detergent. Sometimes you can also do that with ethanol. The methods also differ, depending on what you want to do. If you're just looking for positivity, you don't care if it's on the surface or inside the cell, you can fix first, permeabilize, and then stain, because you're going to stain everything. If you want to see if it's a cell surface or an intracellular, like if you're looking at a CD3, for example, which is located in both places, You might want to stain cell surface first, wash away the antibody, permeabilize, stain again, and then that'll give you a differentiation. Analytical issues. Compensation. Who doesn't hate compensation? Hate compensation. Compensation does my head in, as they say. You can do this pre-analysis or post-analysis. You can let the software do it, or you can do it manually. The recommendation is usually that you do some sort of digital compensation because it's a little bit more accurate. It can be done with cells or beads. Cells mimic the actual assay that's being done. Beads, it can be done with beads as well. It should be done at the time of assay setup and then checked periodically, okay? If your instrument goes down and service comes in and they have to do some major adjustment, you've got to go back to square one and set up that whole compensation matrix again. We want to be, fundamental root of everything we're doing is good science. We have the patient in mind. And then data analysis, I'm not going to go into because you all know how data analysis is done on your instruments, and it varies from instrument to instrument, and there are a variety of offline analysis packages as well. I'm not going to go into those here. Post-analytic. We're in the home stretch. So post-analytic considerations are basically driven by the type of assay. It's a qualitative, or if it's a quantitative, or it's a semi-quantitative. So a qualitative assay is something like I said, is it there or is it not? Is it dim, is it bright? Is it, right? Leukemia assays or leukemia evaluations are like that. They're highly complex usually, multi-parameter. We know this, we're doing multicolor leukemia now. And like I said, it could include information on dim, bright, upregulated, downregulated. It gives you information on change. A quantitative assay gives you an absolute count. If you're doing a CD4 assay, you're getting an absolute count of CD4s. That's a quantitative assay. And semi-quantitative assays usually are looking for something above a minimum. If it's above this, it's positive. Something like PNH, or rare event detection. Storage. We can't just throw this away once we're done running it. What if we're wrong? What if we forgot to do something? What if they need something else done to it? If it's data, we're going to store that as list mode. Store it indefinitely. It should be traceable though. If you store it, it should be traceable. And there are a variety of ways to do that. Your institution will, in all likelihood, have a policy on how to store data and for how long. Samples, usually it's a good rule to keep those 7 days. QA and QC documents, usually it's a good idea to keep those at least 2 years. Maintenance logs, same thing. And SOPs, if you're doing it this way, and that's the rule, and everybody comes to this lab and has to do it this way, and 2 years from now, if something happens, you have that documented. We're in a very litigious society. Unfortunately, that's the way of the world now. But again, all of this is a guideline. You may have certain local regulations and institutional regulations that apply to you. Quality assurance. This is a bit of a nebulous term, but it's very specific. Training should happen. It should be clearly defined, and records of the training should be maintained. Proof, usually proof that the training was incorporated into the person's understanding should also be kept, documented and kept. It's suggested that there's some relationship with an accreditation agency like a CAP, CLIA, JCAHO, etc. External assessments may happen. That may be in the form of an audit. Internally, you might want to do an audit in your laboratory just to make sure that everything is being complied with. There might be an external audit that happens due to some adverse event in the lab. Quality control and proficiency testing. IQC is internal quality control, like Levy-Jennings, temperature control, records, etc. EQC is proficiency testing. I think you're all probably doing CAP or UK NEQOS. That's good to do because it gives you a comparison of how you're doing against your peers, and it ensures precise data. Assay performance criteria. Now you've done all this stuff, now it's time to assess if it's right. Here's where it gets into more of the statistical driven. So you're not on the bench anymore, now you're behind a computer and behind a bunch of notebooks, right? Flow cytometry is classified as a highly complex assay. Anybody that does flow cytometry, this is a big no-brainer, right? Makes sense. You have to know the category of the assay to design the right method validation. You're going to design a method validation for qualitative assays differently than for quantitative or semi-quantitative assays. Validation samples, you might be able to just go online and buy them from a variety of vendors, or you may be able to create them if they don't exist formally. Accuracy is the closest agreement to the average. Okay, so it's like the closest to a reference value. It cannot be established for cell-based assays as defined by ISO 3534. The alternative to this, and this is stated in the guidelines, is that you can compare FCM to expected results. If your smear looks like a CLL and you get a CLL, you have concordance. Specificity. There's analytical and clinical. Clinical is the easy one. It's the ability to tell normal from abnormal. Analytical is the ability of the reagent to demonstrate positivity in the population, to correctly identify the population. There's also sensitivity. Level of background versus level of detection. Level of background is how much background do you have there? What is zero? Level of detection is how close can you get to that and detect it. And it's basically detection of a population. Imprecision. Concordance in interpretation means there's acceptable intra and inter-assay imprecision. Linearity. It's not directly applicable as reportable results for flow are considered quasi-quantitative. The exceptions are going to occur where you're doing things like MRD, fetal red cells, CD64, and this can be done with beads. Carryover is an instrument-dependent phenomenon. So your instrument's going to have a lot of carryover or a little carryover. It has nothing to do with the assay. And you can determine this with beads. You don't have to go through sample to do that. It is important, though, if you're doing MRD or any kind of rare event, PNH, that you have a good idea of your instrument's carryover, or lack thereof, hopefully. Reportable range, that is not applicable to qualitative methods like leukemia lymphoma. Stability. You have to check the stability of your specimen. Not all specimens are stable for the full length of time. So you have to check in your laboratory under the conditions that you're running. if your specimens are good for 4 hours, or if they're good for 6 hours, or if they're good for 1 hour. You know, maybe your laboratory is state of the art, specimens are great for 6 hours. Maybe your laboratory, the air conditioning, so it's very hot inside. Your sample, you might want to run it a little sooner. So you have to, when you set up your specimen's acceptance criteria, check for various time points and conditions that are applicable to your setting. You have to do it on every anticoagulant. So every specimen type, every anticoagulant type, and always check your acceptable range is going to be where a minimum of 80% of the samples are within initial assay imprecision. A processed specimen. So now this is before we processed it, now we've processed it. You have to do the same thing. And set up your acceptance for how long you can use a processed specimen based on time points within your lab that make sense to you. Reagents should always be used according to manufacturer directions up to the expiration dates listed by the manufacturer. You should have in your laboratory assay data for 3 lots of antibody. Reference ranges are defined as a set of values obtained from the analysis of healthy individuals. You can set up reference ranges for your laboratory with your population if you're seeing differences from published literature. So that, in a nutshell, my friends, is validation of cell-based assays. I know I've left you with a lot of questions. I know I haven't covered everything, perhaps something you were interested in covering, but again, I strongly encourage you to go to these links. Reprints of these articles are available free. You can get them from a variety of locations. ICCS, it requires a membership to see the documents, but I strongly encourage you, if you're doing flow cytometry, to become a member of ICCS. There's a plethora of technical documents, educational webinars that are really helpful, not just for validation, but for all aspects of flow cytometry. CLSI is also coming up with a new guideline in preparation called the Validation of Assays Performed by Flow Cytometry. You can go online if you Google that exact term, and you can see a pre-release that was done by Virginia Litwin. I forget where she is now, but she used to be at Covance, and she has a lot of experience with developing tests and assays for pharma. So it's a good resource for you. And lastly, these are the references for the documents, for the phases of validation that I reviewed with you. Each one of these is spearheaded by chair people from that list of 40 that I showed you, with cooperation from others in their lab as well as in international labs. So thank you for your attention.